All right, so the other day we had started talking about 2 and 3-dimensional motion, and I passed out this chart, right? And as I told you guys, find your x and y coordinate after whatever time I gave you, and you did that. And then we discovered that the values I gave you were wrong. You don't care, but what happened was I changed the Excel sheet, but forgot to update the equations, or the other way around. So anyway, if you didn't grab it, in the back is an updated version of that with the correct positions. Good? Yeah. I would keep it because all I did was I reprinted just that piece. You're gonna want the rest of the packet. You know what I mean?
Yeah.
Okay. So I apologize for the mix-up. I feel like I'm getting better. All right. So when you plot all of this data, you get something that looks like this. Something that looks like this. Right? Parametric equation. All right? And so the idea here is each dot represents the position of the object. The position in 2 dimensions represents the position of the object every 0.2 seconds, right? So the first dot is t equals 0. The next dot is t equals 0.2 seconds. The next dot is t equals 0.4 seconds, etc., all the way around, right? Until you get to, I think, 4 seconds at the end. Make sense? All right, so what this blue thing shows us is the path that the drone from Amazon followed to get to my house, right? So it left the Amazon warehouse, and then it went like this, right? But it doesn't tell us anything about how fast it goes. It doesn't give us velocity. It doesn't give us acceleration. It's just, that's the path it followed. Now, you can sort of make some approximations, I guess, about the velocity. So something jumps out at me. There's one point in here where I can see that the thing was moving very slowly. Sure, we got. Say that again? When it was turning at the top. How do you know it's going real slow there? Because dots are close together, right? There's not that much change in position per unit time, right? So that says to me, this thing's not moving very fast, right? Okay? But the problem is that technically you're only looking at average velocity there, right? Okay, so what we need to learn how to do is how to calculate the average velocity of this thing from one time to another, and how to calculate the instantaneous velocity at each moment. And you guys already know how to do that, right? Velocity is just the derivative of the position equation, right? So look, we've got these 2 position equations, right? So if I want to find the velocity at any given instant, what I'm going to do is I'm going to find the horizontal velocity by taking the derivative of this guy, and I'm going to find the vertical velocity by taking the derivative of that guy, and then I've got the velocity in unit vector notation, right? I will illustrate that now. All right? So here, that's sort of where we're headed. So let me embiggen this so you guys can see it a little better. Okay, so average velocity is exactly what you think it is. It's the same as it is for linear motion. Average velocity is just the displacement divided by the time it took to undergo that displacement. Cool? All right. And again, you can write it in component form. Your average velocity is just your average horizontal velocity is your I component. Your average vertical velocity would be your Y component, and your average Z velocity would be your Z velocity. Cool? All right, and so they give an example here. I mean, it's, it says a particle moves through a displacement of 12 meters in the X direction, 3 meters in the Z direction in 2 seconds. So to find the average velocity, you literally just take your displacement and divide it by the time. So you just take each component. 12 divided by 2 gives us 6 meters a second in the X direction. 3 divided by 2 gives us 1.5 meters a second in the Z direction. And there's no motion in the Y direction, right? So there's no J component. All right, so that's a real quick example. That doesn't probably, it's not very insightful probably, right? But that's, kind of the book example. Are there questions with that before I go on to one that's maybe a little more involved? What we're going to do, we're going to analyze the drone's motion and find the average velocity. All right, so are we all good up to here? Okay, stop me if you have questions, you guys, all right? That's why we're here. Okay. So we'll do that in a second. Before we actually do it, though, now let's talk about how the instantaneous velocity is different. Well, again, it's the derivative, right? right? When you take the derivative, you're taking the limit over smaller and smaller time intervals of the average velocity, right? That's really what's going on here. So, here's the textbook definition. It's the limit of the average velocity as the time interval shrinks to 0. Okay? In English, it's the derivative of the position with respect to time. Okay? So that can be intimidating, but literally all you're going to do is you're going to have an expression for the position, the x position. You're going to have an expression for the y position. So you just differentiate the two things. So it's like two problems from last chapter, one for the x, one for the y. Okay? Or 3 if there's a z component. All right. So it tells you to visualize it. Let me jump back to my to the drone thing. Kind of clean up the drawing a little bit here. All right. So suppose I wanted to find the average velocity at, I don't know what time this is, but suppose I wanted to find the instantaneous velocity at that instant. Okay. Well, remember, it's the limit of the average velocity as your time goes to 0, right? So if I was to choose, from time 0, then that velocity vector is clearly wrong, right? So maybe before I go any further, everybody point for me. At that instant, what direction would the velocity point? Kind of this way, right? It's going to be tangent to the line, isn't it? Tangent to the curve, I guess I should say, would be a better way to say that, right? So if you imagine the drone flying around, right? You got to make the sound effect or it won't work. At this instant, it's kind of going that way, right? Does that make sense? So the idea is, as I choose smaller and smaller time intervals, so this first vector clearly didn't work, right? So if I start instead of starting at time 0, if I start my time at 0.2 seconds, I shrink my time interval, I'm a little closer, right? This is certainly closer to that than this was, right? If I start here, it gets better. If I start here, it gets better, right? And you guys can see that, as I draw lines connecting, the smaller my time interval, the closer that vector is going to be to this velocity that we're looking for at that moment. Make sense? Everybody good? Cool. Ethan, is it intentional that you look like Captain Kirk today? Captain Kirk? Is it? It's awesome. I'm a little jealous. I'm not a huge Star Trek fan, but it's spot on. So good job. And if it was an accident and you're lying to me right now, thank you for humoring me. All right. Okay, so that's on the video. That's recorded for all of eternity. All right. Okay, so that's kind of what these little drawings are trying to show you, that as you shrink this time interval, you get closer and closer to that actual tangent line. Cool? Yeah. All right, so let's do an example. I think that's what's on the next slide. So here it's just talking about the notation. This is what I was saying, is that to find your velocity to give an instant, you're taking the derivative of this is your r vector, right? So this is, right, x plus y plus z, right? That's your position vector. So you're taking the derivative of it with respect to time. So that's equivalent to taking the derivative of your x position. That's your I component of your velocity. Take the derivative of your y, take the derivative of your z. Okay. So here's how it's usually written. You say that your velocity is equal to, you've got an x component of your velocity, that's measuring how quickly you're moving along the x-axis. You've got a y component to your velocity, that's measuring how quickly you're moving on the vertical axis. And then you've got a z velocity, which is measuring how fast you're moving, I guess, out of the board, right, or out of your paper, along your z-axis. Okay. And so here it is in shorthand notation, right? The velocity in the x direction is just the derivative of x with respect to time. Y is dy dt, vz is dz dt. So it's exactly what you'd expect. All right, good? Yeah.
So when it's saying dx dt, is that position?
So there's 3 position coordinates right now,
Yeah.
right? Because so here's an example, right? We've got this particle that's floating in space, right? That particle has 3 coordinates. There's an x coordinate, which happens to be -3. There's a y coordinate that's +2, and a z coordinate that's 5. Okay? Now, if this thing was moving through space, you would have a different expression to represent each of those. And you saw that with the drone example, right? Here's an expression to represent the x position of something. Here's a thing, expression that represents the y position of the thing at,
So
different
you're
times.
just taking the derivative of the derivative.
Yeah, in each
So
dimension.
it's not the average velocity.
Correct. Gotcha. Yeah.
If you add those instantaneous velocities of x, y, and z, is that just like total velocity?
Exactly so. Yep, and that's 100%. So now be careful though, when you say add them, how do you add them? Oh, say it again. The Pythagorean theorem, right? Right? Because it's just like, so, I mean, you guys, and maybe you don't know this, but like, here, let me do this. Last year, one of the things you should have learned was that this. If you've got, suppose Roy kicks a football, right? So here's the football, right? Okay, so as it flies through the air, and this is actually the next lecture, the horizontal velocity is constant. Vertical velocity changes because of gravity, right? So at this moment right here, it's got velocity in two directions, right? There's a horizontal velocity, which we'd call Vx, and there's a vertical velocity that we would call Vy at that instant, right? To find the overall velocity, you'd put those together. So that if this velocity happens to be, say, 4 meters a second, and this one happens to be -3 meters a second, then to find your overall velocity, you don't just do 3 plus 4, -3 plus 4. You say, oh, well, I'm moving horizontally 4 meters a second. I'm moving vertically -3 meters every second. That's my overall velocity. So you do the Pythagorean theorem, right? In 3 dimensions, it's the same thing, except you got to use the Pythagorean theorem. Good? Does that help?
So it's the average, like the velocity in all is dx dt squared plus dy dt squared plus dz dt squared.
And then square root of 5, yeah.
Okay.
Right, to get rid of the
Yeah.
v squared, right? Yeah, so that's, I mean, all you're doing there, that's what we learned last chapter. That's what you just took a test on, right? That's how you find the magnitude of the velocity, right? You'd have this velocity vector that's written in terms of, and all of this, you're going to see this in a concrete example, and I think that'll make your life a little bit easier. Oops. So like here's my, it's an average velocity, but same idea. So this average velocity has an x component and a z component, right? So how do you find the magnitude of that thing? Well, you just use the Pythagorean or Pythagorean theorem, right? So that's all we're doing. Let me do an example, and I think you guys will be like, oh, I see. All right? Okay, so I think we're good up to here. Okay. I wasn't planning on spending time with this, but maybe it's worthwhile. Maybe let's take a second on this. All right, so this is, again, just stolen out of the book. So it says, checkpoint 1, the figure shows a circular path taken by a particle. If the instantaneous velocity of the particle is v equals, and then, so here's our velocity. So our velocity at a given instant is 2 meters a second times our x unit vector minus 2 meters a second times our j unit vector. And then it wants to know through what quadrant it's going. But so do you guys understand, how would I find the overall velocity of this thing? What this is telling me is that my object is moving horizontally at 2 meters a second, and it's moving vertically at -2 meters a second. So the overall velocity is v. So you'd have to, do the Pythagorean theorem. It's what, 2 root 2? So whatever that is, but that would be your velocity, right? Okay. So if it's moving in a circle, right? It says it's following this circular path. It wants to know if it's going, so the first one is going clockwise, so this way. So if it's going clockwise, at what point on the circle could this be the velocity? Which quadrant? 1, 2, 3, or 4? Quadrant 1, right? Because I want the point when it's going this way. So if it's going clockwise, it happens right there, right? Does that make sense? What if it's going counterclockwise? Then it's going to be here, right? Make sense? Because the velocity is always tangent to the path that it's following, right?
Because the 2 and it's -2, can you assume that 45 angle from the X.
Say that one more time.
So
I mean, yes, it's got to be 45 degrees. I don't know
right,
if this is...
but can you respect this movement though? Like,
Yeah, yeah. And that actually is because of, that's more a property of circles.
right.
Because if this was an ellipse, it wouldn't necessarily be at 45 degrees. But yes, you got the right idea. Okay. One more time. The instantaneous velocity, correct? Yeah, it applies to 1 point, one exact instant in time. Good? Is everybody good? Any questions? Okay, cool. So, back to our Amazon drone. All right, so we're going to actually do an example. And I hope that this will sort of tie everything together for you. All right, so it says a drone from Amazon is delivering Mr. Hecker's new pogo stick. This is all the same thing we had before, right? So here's an expression for the horizontal position of the drone at any given moment. Here's an expression for the vertical, right? So here's our horizontal. Here's our vertical position at any given time. Now, I already know, I don't know that you have to do this, but just to make a point, check it out. Suppose I wanted the position after 2 seconds. What would I do? Plug 2 into X and Y and solve it, right? And we've already done that. You guys have it written down in front of you, right? That's what that big chart was, right? So this is just a side note. You don't actually need this to solve the problem, but I just want to make sure you understand. So if you plug 2 in, your X position ends up being, somebody have it? I can flip back in the slides, but what is it? 3. So I'm going to get 3, what are my units here? In miles. So 3 miles times I plus 0 is the Y. Okay. So 0J, I guess you don't really have to write it. But so there's your position after 2 seconds. Make sense? So that was on my map. It looks like that's right here, right? T equals 2, right? Because that's where the X is 3 and the Y is 0. Follow? All right, so now let's find the velocity. So before we do, my velocity, whatever it is, it looks like it should have a big negative Y component and a very small horizontal component, right? Because most of the motion is north to south, right? And there's not that much progression east-west. Follow? All right, so let's actually do this and see what happens. Okay, so can I erase this little note about the position? All right, so let's find our dx dt. So the derivative of x with respect to t, that is our velocity in an x direction. That's what that represents. That's why I'm finding it. It's telling me my horizontal velocity. So I'm just going to take a derivative. So let's see, I got to bring down the exponent, right? So I'm going to do negative 1.5 times 3. So that's negative 4.5 t squared plus 12t minus 4.5. And I'm being sloppy about my significant digits. I probably shouldn't be, but... And I got to be better about making my decimals a little darker. All right, so is everybody good with that? All right, now I want it after 2 seconds. So let's find Vx after 2 seconds. What do I do? Just plug in 2, right? So let's see. 2 squared is 4 times negative 4.5, so that's negative 18 plus 12 times negative 2 is negative 24. Oh, sorry, positive, thank you. I'm starting to get nervous. 24, and then minus 4.5, right? So what's that going to give me? 1.5, I think? And then my units are miles, because the problem told me that the position is in... Oh, no, it's not. It's miles. Does it tell me? Oh, miles per second. All right, well, it is what it is. Is it hours? Oh, hours and up here. Oh, crud. Shoot. Hours. Sorry about that. All right. I was wondering. Okay, so we're finding the velocity after 2 hours. That's my bad. Thank you for calling me out. It's a freaking fast drone. All right. Is everybody good with what we just did? So this is telling me after 2 hours, apparently, my drone is moving horizontally east 1.5 miles an hour. How do I know it's east?
Positive.
Positive. Okay? So now I'm going to repeat the exact same process for the y component. So dy dt, that's going to give me my vertical velocity. What do I hope will happen? What
It'll be very negative.
should be very negative, hopefully. So let's see if it works. So let's see. I'm going to take my derivative. I'm going to get 6t squared minus 24t plus 16, right? Why do I want it to be very negative? Because the picture shows me that after 2 seconds, most of the motion is in a vertical direction. Cool? All right, so fingers crossed. Always, I know. Yeah, I hear you. All right, so no, you're right though. You're right. Everything should be hours. All my time units should be hours. Okay, so everybody good with how I got my Vy?
Yeah.
So now let's find our Vy after 2 seconds, or 2 hours. Hours, man, that's gonna. Okay, so I'm gonna plug in 2. So let's see, 6 times 4 is 24, minus 48, plus 16, right? So 24 and 16 is 40, minus 48, I get negative 8 miles per hour. Cool. So now I could find the overall velocity by just drawing a little triangle, right? So the velocity is, you could either write it in unit vector notation, which would be 1.5i minus 8j miles per hour. Or you could do Pythagorean theorem and find your angle and then write it in magnitude and direction notation. And either one would be fine. They're both accurate. Cool? Yes?
Since we're using the Pythagorean theorem to find the hypotenuse, wouldn't it always be positive?
Yep, but then my direction would be some number of degrees south of,
Okay. So
South of east.
You have to report the direction.
correct. Yep. So, shoot, I wish I had a little bit more room here. There we go. How about that? So, all right. Are you good? Do you want me to go through it, or are you good? Do it? Yep. Okay. So, this, what I'm up here. We'll come back to that in a second. All right? So, or we can write it this way. We can say, all right, well, my horizontal velocity is 1.5 miles an hour. My vertical velocity is negative 8 miles an hour. Here's my hypotenuse. So I'm going to grab a calculator and find the hypotenuse. So let's see, and I want the square root of 8 squared plus 1.5 squared gives 8.13. What do we got? 2 significant digits here, so 8.14 miles per hour. But that's not enough, because remember, velocity includes direction. So now I need to say at, so here's my compass bearing. So this is east, and we are some number of degrees south of east. So which trig function should I use, you guys? Inverse tangent, right? So I'm going to do inverse tangent of 8 over 1.5. Okay? Thank you for asking, by the way, Carson, when you had a question. So inverse tangent of, I'm literally just doing inverse tangent, second tan of 8 divided by 1.5. 8 divided by 1.5. And it gives you 79.4 degrees. And then it's going to be south of east, right? South of east. So that and that are equivalent ways of saying the same thing. Francis, you said, shouldn't we? Yeah, so you don't need to worry about the negative because that's sort of taken care of when we say south of east. If you put a negative in, it'll just give you negative 79 degrees, and then you just go, oh, well, you can't have, you know what I mean? It's like a double negative. Yeah, Alex.
So, is the unit vector notation and the velocity notation, like, are those interchangeable?
Yeah, I mean, it's 2 different ways of saying the same thing. Like
Yeah.
1/2 and 0.5 mean the same thing. One's fraction, one's
okay.
decimal.
You can write it either way.
Yep. Yeah. Usually on the homework, if I say find the velocity, usually I'll give it this way, and if I want it in unit vector notation, I'll say in unit vector notation. Yeah, so let's make that our standard, you guys. If it doesn't say unit vector notation, assume that I want magnitude and direction. Fair? Yep. So when I'm asking a problem on a homework assignment, the problem will say either find the velocity after 2 seconds, and I'll want this, or it'll say in unit vector notation, find the velocity after 2 seconds, and then I want this. Cool? All right, are you good with how I found the angle? All right. Francis, did I answer your question? Is everybody good? Is anybody ungood? Okay, awesome. All right, so now let's go back and find our average velocity. So can I erase all this garbage? Oh, that's not at all what I wanted to happen. Okay, cool. So now we got to find our average velocity. So look, average velocity is change in position over time. I already know my time is 2 seconds, right? So t equals 2 seconds. What's my initial position, you guys? Oh, I guess I should write RO, shouldn't I? R0. So the starting position was 0, right? And then a minute ago, I had written down what the position was after 2 seconds. So the position after 2 seconds, I'm going to use this notation R2, meaning the position after 2 hours. Sorry, I keep saying seconds out of habit. Everybody good? You could also write it this way, R after 2 hours. That would be probably more notationally correct, but yeah, Mickey?
You also write it as C2?
No, we're going to, well, I mean, I guess technically a lot of things do use D for displacement. This isn't displacement though, it's position. So usually we use X for position, but now we've got 3 components to take care of, X, Y, and Z. R represents X, Y, and Z all as one vector. Cool? It's R because it's the radius from the origin. I should have said that yesterday. All right, or 2 days ago. So that's why it's R. Did I say it? Okay, cool. But yeah, so that's why it's R. It's telling you the radius from the origin. Cool? All right, so we figured this out. What was it? 3I miles? Isn't that what it was after 2 hours? Cool. So what's my change in position going to be? This one's really easy. It's 3I minus 0 over 2 hours. And so you get 1.5 I miles per hour, right? Here, let me do this. I see somebody squinting. Nope, that didn't help. There we go. Yeah, Alex.
Is that only the velocity in the x direction then?
It's overall, because it happened just by coincidence. After 2 hours, our position, and I'll show you pictorially what was going on in a minute. It happened that after 2 hours, our position was on the x-axis.
So,
Oh, so it would be like 3I plus 0 j.
Exactly, 3i plus 0j. Yeah, so if there had been a j, you would just treat that as one more thing.
What would you do with that?
Sorry? Hang tight for 1 second. I'm not trying to ignore you. Is everybody okay with this? Alex, are you good to answer?
I just thought the same method.
Let me show you pictorially, and then I'll answer your question, Ethan. I'm not trying to ignore you. Oh, shoot, I lost my... Where's my little... Oh, thank you. I'm standing in the shadow. All right, so pictorially, here's why that happened. After 2 seconds, we were here, right? So my R is this. So I went east 3 miles in 2 hours. So I went east an average of 1.5 miles an hour. Cool? Follow? All right, now, what if it hadn't been that? What if there had been a J component and a K component? Well, then that's this stupid book example. So if my change in position had, I'll make up an example. How about this? Okay. So suppose I'm just going to make up some random numbers. An object goes from So it goes from that starting position vector to whatever. How much time do you want that to take? About, we'll do 2 seconds because it's easy to divide by 2. Good? So I'm just giving you a starting position, an ending position, and a time. Follow? Starting position, ending position, time to get between them. So V average is my change in position divided by the time it took, right? So let's see, our change in position. So I'm going to take this position vector, 2i plus 3j minus 4k, and I'm going to subtract this position vector, and divide it by the time it took. Good. I'm just going to scroll down a little bit.
So that would be because you don't make a straight line. You don't use like displacement. You would just use the
Well, I mean, you are. So this is a point in space, right? Maybe it lives here. And this is some other point in space that lives here. So what I know is during those 2 seconds, I traveled from here to here, right? So this top part of the fraction is giving me the straight line distance between these 2 points. Straight line, right?
Okay.
And then I'm just dividing by the time it took. Except I'm leaving it in unit vector notation. Average speed is way harder to find because then you got to know the length of the path that you traveled to get from here to here, and that's ugly. We're not going to mess with that. Okay. Because you got to know, and I honestly would have to look up how to do this. You'd have to use calculus to find the length of a curve, and I know I've done it before, but I don't remember how off the top of my head. Yeah.
You used would that be like X? And
Exactly. It's like xi and xf.
Or like with that, because you have two equations would be how far you went in the X direction and then.
So this is so in that example, this would be my initial x, this would be my final x.
Okay.
This would be my initial y, this would be my final y. Initial z, final z. Good? So what I'm about to do now, you guys, is this. So I'm going to subtract component-wise. So 2i minus 3i, that's negative 1i. That means horizontally, I went to the left 1 meter, right? And 3j minus negative 6j, I went up 9y units. Follow? And then negative 4 minus 5 also gives me negative 9. So I went down, or whatever, into the board 9z units. And all of that took 2 seconds. This was all in meters, right? Good or no? Mickey, how you doing? You good? Good. Nathan, how about you? You good? Sam? So then you just divide it out. So negative 1 divided by 2 is negative 0.5i. 9 divided by 2 is, yeah, sorry, I was just giving myself more room, but thank you. Plus 4.5j minus 4.5k, and then my units are meters per second. So this is my average velocity vector written in unit vector notation. Horizontally, I averaged negative 0.5 meters every second. Vertically, I averaged, cool? Mickey?
We mostly be giving us a problem where you give us an initial position for 2 equations.
You should be able to do both.
So you give us like a mix of both.
Yeah. totally, yeah. I mean, it's AP, you're gonna get, it's totally just wild card, you know what I mean? Jake, thank you, I wanted to say Jack, I was wrestling.
For like one like this, do we have to use like the south or east or something like that, or how do we do that?
You really good question. It's very difficult to describe direction in 3 dimensions. So either I'll just say what's the magnitude, or you can just leave it in unit vector notation. Good.
Staff and students, announcement in